Merci beaucoup de m'avoir invité. Je vais faire ce colloquium en anglais parce que mes transparences sont en anglais et ce serait un peu maladroit à donner une traduction simultanée. So I'll be talking today on mass, scalar, curvature, Kähler geometry, and all that. And because this is a colloquium talk, I've tried to make it very self-contained, so I hope that everyone will come away having learned something. So that it's just that different parts of the talk may appeal to different segments of the audience. Let me begin. Well, I guess I should first say that some of the core results that I'll eventually discuss in this talk are joint with Hajo Hein of Fordham University in New York, and can be found in our joint paper, Mass and Kähler Geometry, which was published in Communications in Mathematical Physics. But I'll also implicitly discuss some recent technical improvements which allow some of the statements of the results to be simplified. These technical improvements can be found in a more recent paper, Mass, Kähler Manifolds and Symplectic Geometry, which appeared in the autumn on the archive, and which will appear in the Annals of Global Analysis and Geometry. In fact, there's already an online first version of the paper available. On the other hand, the archive is definitely free, so it may be an easier version. If you go to my homepage, you'll find a link in order to be able to read it for free. It's kind of nice. These Springer Nature sharing apps allow you to make a paper available for free, even to people that don't have a subscription to the journal. So I'd like to begin with some of the rudiments of Riemannian geometry. Remember that a Riemannian manifold is a smooth manifold that has a positive definite inner product on every tangent space that varies smoothly from point to point. And one of the key ideas in the subject is that there are curves on a Riemannian manifold called geodesics, which have the property that for sufficiently nearby parameter values, the curve minimizes the length. It's the shortest curve between those points. It turns out there's a unique geodesic in every direction, so there's a so-called exponential map, which you can define. In general, it's only on a neighborhood of the origin in the tangent space at a given point. We're going to choose a base point. And there's a map which, for historical reasons, is called the exponential map. Don't ask me right now why it's related, what it has to do with the usual exponential function. This map is the map which, given a tangent vector at the base point, follows a geodesic in that direction for a distance, parameter distance, which is the same as the as the length of the initial tangent vector. So this, if the manifold is compact, this is actually defined on the entire tangent space. More generally, if it is complete in the sense of metric spaces, this will be defined on the entire tangent space. In general, this may only be defined on a neighborhood of the zero vector in the tangent space at P. But the important point is that that actually, if you restrict to a sufficiently small neighborhood of the zero vector at P, this is actually a diffeomorphism between a region in the tangent space and a region in the manifold. And that's to say that the Riemannian metric, once you choose a base point, there are actually canonical coordinates. So a manifold, of course, is something that's diffeomorphic to Euclidean space, but there's actually a way of constructing a sort of God-given diffeomorphism in the presence of Riemannian metric. So if you choose an orthonormal basis for the tangent space at the base point, you can actually then say, well, the tangent space looks like Rn as a vector space within a product, and now you've got some very, very standard coordinates near the given base point. So one could ask, well, in this coordinate system, what does the given metric look like? And the idea behind this really goes back to Riemann. who, without building up any machinery, discovered what we now call the Riemann curvature tensor. The point is that if you write down the metric in these preferred coordinates, to lowest order, it looks like the Euclidean metric, where if you think of the metric as just given by a symmetric n by n matrix, it looks like the identity matrix plus, and then you can look at the Taylor expansion of the components of the metric in this coordinate system. And there's no linear term. The first non-trivial term is quadratic, and then there are cubic and higher order terms. So Riemann realized that this quadratic term is typically non-trivial, and that it actually gives you a natural invariant. Of course, it depends on the place, the point P that you choose as your base point. So you'll have a different system of coefficients for different points. In fact, Riemann had a very natural way of thinking about this as without really building up any of the modern machinery of tensors. He had a way of understanding the structure of this object. So the components Rj, Lm, Km here are called the components of the Riemann curvature tensor at the reference point P, or the base point P that we chose. And that's represented in these coordinates by x equal to 0. Now actually, in order to say that these components are uniquely expressed by this, are uniquely determined by this expression, you have to impose some symmetry conditions. The usual ones are not quite obvious. They're called the Bianchi identities. And so if you impose certain algebraic symmetry constraints on these coefficients, then they're uniquely determined by saying that this gives the quadratic term in this Taylor expansion of the components of the metric. Now, there are certain components where, so here, in general, these depend on 4 integers from 1 to n. The convention, though, is, for example, this is antisymmetric in exchanging j and l, and antisymmetric under exchanging k and m, and then there's a less obvious so-called Bianchi identity. But on the other hand, so terms like R11 anything would be 0, but R12, and if you repeat 1, 2, that gives rise to something which, if you look back at the meaning of this expansion, it's actually asking if you take a 2-plane in the tangent space and you spray it out by the exponential map, that gives you a surface. And you could ask, what's the Gauss curvature of that surface? This would be the Gauss curvature of the surface that corresponds to the first spanned by the two first basis vectors in the tangent space. So there's a more synthetic version of this called the sectional curvature, which contains all the geometric information of the Riemann curvature tensor. So the sectional curvatures are, the sectional curvature assigns to every 2-plane in any tangent space on the manifold a real number. Geometrically, what you do is exactly what I've just said. You take a 2-plane in the tangent space at some point, spray it out by the exponential map, look at that as a 2-dimensional surface, and it has a Gauss curvature. What does the Gauss curvature actually measure? Well, one way of thinking about it is if you take a triangle that you would make an isosceles triangle in the manifold by taking some 2 vectors that are separated by a very small angle, go out a short distance epsilon along both of these directions, and then you would have an isosceles triangle. You could say, what's the distance between the endpoints here? And it turns out that this distance, if you compare it to what you would get in Euclidean space, to lowest order, it's 1. And then there is a quadratic deviation. So the quadratic deviation has a coefficient, and that's this sectional curvature, which is, in the case of a 2-dimensional manifold, it would exactly be the Gauss curvature at that point. But in higher dimensions, it depends on which 2-dimensional plane you choose in the tangent space. All right, and the convention, by the way, is that like if you think about just the geometry of the 2-sphere, on a 2-sphere, you would actually see that the distances are less than they are in Euclidean space. In something like hyperbolic space, which is negatively curved, the distances are greater. So this distance would be, if k is positive, this is shorter than it would be in Euclidean space. If k is negative, it would be greater. Okay? So a metric is said to be flat if it satisfies the condition that its sectional curvature is exactly 0. That's the same as saying its Riemann curvature tensor is 0. And that's equivalent to saying that there are local coordinates near any point in which the metric exactly becomes Euclidean. Now, the main reason for mentioning this is I want to look at other flavors of curvature. This is the Riemann curvature I've just described. It may be conceptually simple, but it actually is a very complicated object, and it takes time to get your mind wrapped around it. There are some other kinds of curvature of a manifold which give curvature information about the manifold in a more simple guise. So for example, we could, instead of asking about distance in the manifold and how do distances compare when we look at these special coordinates given by the exponential map spraying out by geodesics, you could instead ask what is the volume measure determined by the metric g versus the volume measure determined by just the Euclidean metric on the tangent space. So this volume measure is actually a smooth measure, and so these two things there'll be some smooth function that fits in here. Actually, geometers usually talk in terms of n-forms rather than measures. The key difference is that a form has the property that an n-form would have the property that it depends on the orientation of the manifold, whether it's positive or negative. However, if you're not happy with that, just think about there's a volume measure determined by the metric, and there's a volume measure, of course, a familiar one on Euclidean space. How do they compare? If you look at a Taylor expansion of the coefficient to lowest order, it's 1. And then there's a quadratic deviation, and then there are terms that are cubic or higher. And so this quadratic piece is just in the most naive term, there's an n by n symmetric matrix of coefficients here, but more abstractly, the point is that there's a natural quadratic form on the tangent space which encodes this information. And it's called the Ricci tensor of the manifold. We often think of it in terms of the associated symmetric bilinear form that it determines, which is called the Ricci tensor. And this object is actually related to the previous Riemann curvature tensor as a trace. It's related to the fact that when there's a famous formula for if you take the determinant of 1 plus epsilon times a matrix, the term that's linear in epsilon is the trace of the matrix. Or if you like, the trace is the derivative at the identity of the determinant. I didn't really tell you what the formula for this volume form is. It's characterized by the fact that if you feed it an oriented orthonormal frame, you get 1, but that when you actually write that out in coordinates, it takes this form. It's related to the coefficient is the square root of the determinant of the matrix that represents the matrix, the metric. All right, so more conceptually, you can think of the Ricci tensor as a function on the bundle of unit tangent vectors, and it encodes the way whether the degree to which the exponential map fails to preserve volumes. So more abstractly, you might say, let's take a small cone truncated at distance epsilon in the tangent space. Assume it's a very narrow cone that's focused, that's nearly points in the direction of a given vector. And provided this is a very tight cone, if you were to ask what would be the volume in Euclidean space versus what you actually see in the manifold, you get a quadratic deviation that depends on the direction of the vector. And in fact, if you think about it in the right way, you should think about this as given by, it's a quadratic form on the unit tangent vector. The key point is that volumes, if the Ricci curvature is positive, volumes in the manifold will be less than they would be in Euclidean space, and at least nearby the base point, if the Ricci curvature is negative, then volumes will be greater. A metric is said to be Ricci flat if it satisfies the condition that the Ricci tensor is identically zero. This is a famous, much studied equation in the context not of Riemannian manifolds but of Lorentz manifolds. It was first introduced by Einstein as the candidate for the equations for gravitation in the vacuum. And by the way, why do most Riemannian geometers do not know why do they call the metric G all the time. It's Einstein's notation. It means gravitational field. For Einstein, G was the gravitational field. All right, so this is still complicated, but there is a simpler version of the curvature that you can really explain without being terribly formal or not. So, of course, so the Ricci tensor was discovered by Ricci Curbastro without, just as a kind of formal useful thing that you could calculate, but he didn't think about what does it mean in terms of comparison geometry. The story I've just told you would have been a little bit alien to Ricci. He also introduced this thing I'm calling the scalar curvature. It was originally called the Ricci scalar, and the notation is that I'm using is quite different from what was done in classical differential geometry, where all curvatures were called R, and you only knew which kind of curvature it was by how many indices it had on it. Of course, here I've written some indices, so the distinction is not perhaps so important. But the scalar curvature has a very simple geometric description. So it's a function on the manifold. In some sense, it's the closest analog to the Gauss curvature of a surface. A Gauss curvature is just a function on a surface that tells you something about the geometry. Scalar curvature is a function on the manifold that tells you something about the geometry. And what does it mean? It arises when you compare the volumes of balls in the manifold to the balls in Euclidean space. And what do you mean by a ball? Well, you could say it's the image of a small ball in the tangent space under the exponential map. But it's a remarkable fact that that's exactly the same as the set of points that you can reach by curves of distance less than epsilon. It's a non-trivial lemma in a first course in Romani and Geometry. So the volume of a ball in this sense, divided by what you would see for a ball of radius epsilon in Euclidean space, again has an expansion, which it looks like 1 plus some quadratic term. Conventionally, well, because of the history of how these things are invented, the coefficient is chosen to be negative here, and there's a weird numerical coefficient depending upon the dimension that arises here that has to do with the fact that Ricci, Curbastro, and so forth, they were not thinking about what does this mean geometrically. It's just something they knew how to calculate. But it has this beautiful meaning. If the scalar curvature is positive, it means a small ball has less volume than it would have in Euclidean space. If the scalar curvature is negative, it means that a small ball has more volume than it would have in Euclidean space. And a metric is said to be scalar flat if the scalar curvature is identically zero. All right, so now you've met a few types of curvature, the main ones that people study in Riemannian geometry. So here's a typical example of a problem that's harder than you might think. Suppose we look at a complete, this is complete in the sense of metric spaces. That's also the same as saying that GD6 can be extended to run forever. Suppose you have a non-compact, complete Riemannian manifold of dimension n, and it has the following curious property. Suppose that after you cut out some compact set, it actually looks exactly like Euclidean space minus a ball. Now, it's very easy to write down lots of Riemannian manifolds like this. I take Euclidean space, I cut out a ball, then I just glue in any manifold I like. As a topological manifold, as a smooth manifold, the kind of manifold I'm looking at is just you take a compact manifold without boundary, throw out one point, and then stretch out a neighborhood of the point so it looks like Euclidean space, okay? So there are lots of possible topologies. Here I want to suppose that the metric looks like exactly like Euclidean space outside of some compact set. So far, there's certainly no obstruction to writing down lots of such things. But, okay, so it's this strange modification of Euclidean space where we haven't changed the metric outside of this compact set. But here's an interesting question. Suppose that this manifold has non-negative curvature. Can you find any examples which are not flat? Or, in fact, it'll turn out that with various interpretations, the conclusion is that it has to be flat, that you couldn't have modified the manifold in any essential way. So, for example, if you had put in the hypothesis that the sectional curvature of this manifold is greater than or equal to 0, and it'll turn out that you cannot do this if you've made any real modification. The only possibility is this manifold would have to be literally Euclidean space. And so, for example, a classical way of doing this might be to use distance comparisons. But I've said there are different kinds of curvature. What if you assume that the Ricci curvature is greater than or equal to 0? Does that imply that this manifold is flat? So it's certainly flat out here. It's exactly Euclidean space out here. Is there any real modification you could make while keeping the Ricci curvature non-negative? So it turns out you can't. The only possibility is that it's actually Euclidean space at the end. And one way of doing this is in terms of the famous Bishop-Gromov volume comparison, because the volume growth, for those that know this, you're looking at a simple argument, it would be that the volume growth asymptotically is the same as in Euclidean space, and for when the Ricci curvature is non-negative, that only happens for Euclidean space. But the hardest, these problems, so they're sort of very, very standard techniques for solving these problems up to this point. What happens if we assume this manifold is non-negative in the sense of scalar curvature? The scalar curvature is greater than or equal to 0. Can you still prove it's flat? Well, the answer to this in complete generality was not known until last year. The answer is this is a much harder problem, and the answer turns out again to be yes. The only way that you can arrange in this setting, if it's Euclidean space outside of a compact set, the only way that you can arrange for the scalar curvature to be greater than or equal to 0 is to fill it in as Euclidean space. So even though it turns out the scalar curvature is a very, very weak invariant, it doesn't contain very much local or global information about the geometry, and yet you can actually prove very, very strong results if you work hard enough, just that involve only scalar curvature as a hypothesis. In fact, the inspiration that leads to the solution of this question comes from physics. And the relevant theorem is, this is a special case of what's called the positive mass theorem. And in fact, the positive mass theorem would give you the same conclusion that the space is actually Euclidean space, even without assuming it's exactly Euclidean away from this compact set. But in fact, it would be enough if the metric fell off fast enough to the Euclidean metric and still had non-negative scalar curvature. You would still get the same conclusion. So let me now introduce an important notion. A complete non-compact Riemannian n-manifold, and here this is a fake picture. I'm always going to assume that the dimension is at least 3, but, well, sometimes a fake picture is better than no picture at all. All right, so we're assuming the dimension is always, the real dimension is always at least 3 from now on. Okay, so such a thing is said to be asymptotically Euclidean, or AE, if there is a compact set such that its complement is diffeomorphic to Euclidean space minus a closed ball in such a manner that, well, this, you can think of this as a coordinate system, and you say, well, in these coordinates, what does the metric look like? Previously, I was imagining maybe the metric was exactly Euclidean out here, but we're going to say it's going to be Euclidean plus terms that fall off at infinity. And part of the difficulty of the subject is finding the right precise hypotheses. What do you mean by it falls off fast enough at infinity? The weakest reasonable assumption was discovered by the mathematical physicist Piotr Kruszwil, and his assumption is that the metric and differs from the Euclidean metric in these coordinates by terms that fall off a little bit faster than 1 over the radius to the half the dimension minus 1. And then if you were to naively imagine that this was exactly a power of the radius and differentiate once, then you would say we expect the first partial derivatives would fall off like 1 over the radius to half the dimension, or a little bit faster than that. So here epsilon is some positive constant, but arbitrarily small. It could be arbitrarily close to 0. And finally, the other hypothesis is that the scalar curvature, remember we talked about the scalar curvature before, is L1. In other words, the absolute value of the scalar curvature is supposed to have finite integral. So the scalar curvature, when you actually compute it, involves 2 derivatives of the metric. So the main hypotheses here involve the value of the metric and its first derivative. The second derivative only comes in this more geometrical assumption that the scalar curvature, the absolute value of the scalar curvature has finite integral. Now, I lied to you slightly in the definition, because I've assumed beforehand that if we took out this compact set, there'd be only one connected component left, and that connected component would look like Euclidean space minus a ball. But it's actually useful to generalize the definition to allow the manifold to have many ends. So topologically, rather than looking like a compact manifold minus a point, it might be a compact manifold minus a finite number of points. And then neighborhoods of these points are sort of stretched out to look like Euclidean space. And so we require that a compact set has complement consisting of some finite union of copies of Euclidean space minus a ball, in such a where under these you assume that there exists some diffeomorphisms in which the metric then has this kind of good fall off. So it looks in this precise sense like the Euclidean metric plus terms that fall off quickly at infinity. All right, and then one refers to these different connected components as the ends of the manifold. There's a more general notion of the end of a non-compact manifold, but this will do for the purposes of this lecture. All right, now comes the weird thing which fell out of physics. One associates to each end of an asymptotic Euclidean end manifold a number which is called the mass. And it's defined in the following very peculiar coordinate-dependent way. You begin by looking at the divergence of the metric minus the gradient of the trace of the metric. You then, in these coordinates, you look at the outward pointing component with respect to the Euclidean outward pointing unit vector, and to integrate that on a large sphere of radius rho with respect to the Euclidean area form, and now take the limit of that expression times there's a conventional constant which people tend to introduce, this coefficient in magenta, you can ignore it if you like, and you take the limit of that as the radius goes to infinity. So here, the thing we're integrating on is diffeomorphic to the n-1 sphere, and in these coordinates it's simply a sphere of large radius. and then we're taking the outward pointing normal of that sphere with respect to the Euclidean metric, and we're then reading off the component of this expression and then integrating that against the Euclidean area form. This is a very strange thing. I mean, why is this coordinate independent? If you have an asymptotically Euclidean manifold, you can certainly find many different compatible sets of coordinates. This looks like some strange alien expression. It's like you get a signal from outer space, and it's something like this, and you don't know how to interpret that. But independently, Crucial and Bartnik showed in 1986 that this mass actually, with suitable weak fall-off conditions, this mass is first of all well-defined. I mean, that's to say this limit is well-defined, but it's also coordinate independent. Bartnik's fall-off hypothesis is stronger than Crucial's, but then he proves a somewhat stronger coordinate independence. But the Crucial hypotheses are the ones I'd like to use because they, first of all, they're much less technical. And Bartnik worked with weighted Sobolev spaces of functions in order to the key thing is he needed to show that you could find preferred coordinates by demanding that they be harmonic. All right, so Crucial's hypotheses are exactly the ones that I've shown you. And what he showed was simply that this mass is invariant under a large class of coordinate changes that preserve. It's literally independent of coordinate changes that preserve the fall-off type of the metric. Now, where does this come from? It came out of gravitational physics. And specifically, it was invented by Arnowit, Deser, and Misner in the case of when our Riemannian manifold has dimension 3. General relativity has to do with, not with Riemannian manifolds, but with Lorentz manifolds, where the inner product is not positive definite. However, in a four-dimensional space-time, you can find hypersurfaces which are so-called space-like hypersurfaces where the induced metric is Riemannian. And that would be choosing space out of space-time. The idea of Arnowit, Deser, and Misner is to choose such a slice and then try to associate a number. If the metric falls off to the Euclidean metric to the Euclidean metric fast enough on the space-like slice, and in practice, that's usually saying that the Lorentz metric falls off to Minkowski space at infinity in the right way. Then you want to associate some number which would represent the. You think of this Lorentz manifold as being some model of the universe where all of the mass is kind of concentrated in a small region. And now you could sort of say, well, out at infinity, gravity is pretty much like Newtonian gravity. What would be the apparent mass of a system with this property? So it's trying to read off the number which would be the apparent total mass as seen from infinity of this gravitational system. And you could try to measure that, for example, by orbiting a particle pretty far out from it and saying, well, this is acting like it has how much mass inside. So here's a key example. And by the way, there was a weird normalization constant I put in before, and which, without any explanation, it was shown in magenta. The key example that sets what that normalization constant is a so-called Schwarzschild model. So this is the n-dimensional. This is the generalization to n+1 space-time dimensions of the standard model for a non-rotating black hole or a non-rotating gravitational source of any type outside the region where there's mass. So here I've written down the Lorentz metric. As you see, this is not positive definite. This metric is negative in some directions, and that's why I have a different font for the metric. If we restrict so there's a variable here which actually you can think of as time, or it's a particular coordinate time. If you now set that equal to 0, you get a space-like hypersurface. And here the manifold that it's defined on is an n-1 dimensional sphere times an interval in the real line, So you could think of that as being diffeomorphic to the exterior of a ball in Euclidean space just by taking polar coordinates. And if this was exactly Euclidean space, this coefficient would be 1. But in the Schwarzschild solution, you have to change this parameter by replacing this by 1 minus 2m over the radius to the space dimension minus 1. So in the most familiar physical case, n would be 3, and this would be 2m over the radius. Now, when I defined the mass before, I always imagined that I was talking about a complete Riemannian manifold. This is not complete written in this form because it's just on the exterior of a ball. But it turns out the place where this goes bad is when this power of the radius is equal to 2m. That's called the event horizon. And if you glue together two copies of this Riemannian manifold, you get a remarkable complete Riemannian manifold. It's really like the black hole seen from two different universes. So there's a region which looks pretty much like Euclidean space, and then you find that there is a smallest hypersurface here that looks like the n-1 sphere, and the size of that hypersurface is a measure of the size of this neck. Now, this particular metric is actually scalar flat. It has zero scalar curvature. That's related to the fact that the space-time has Ricci curvature 0, and this is a totally geodesic hypersurface. And it has two ends. It happens that the mass is the same on both of those ends. What is the mass? It's this number m. So as I want to emphasize, this is not a Ricci flat, even though it's related to a Ricci flat Lorentz manifold. It's a scalar flat, but not Ricci flat Riemannian manifold. Interestingly enough, it's not only is it scalar flat, it's also conformally flat. The metric looks like Euclidean space-time as a function. Most metrics don't have that property when you're above dimension 2. And so it has the same mass at both ends, which somehow is related to the size of the throat. Here, there's a different way of writing this metric now as explicitly the Euclidean metric on Rn minus the origin. So here, one end here actually is near the origin in these coordinates, and the other end is near infinity. And so here we have Euclidean space minus the origin, and now here this is the Euclidean radius. So we have 1 plus something that blows up at the origin. This function is not an arbitrary function. The thing we're adding on here is the Green's function for the Laplacian in n dimensions. And there's an amazing story called the Yamabe equation that relates the Laplacian. There's a Laplace-type equation, which if you start at a scalar flat metric and you want to go to another scalar flat metric, it turns out that that's saying you have to multiply by a certain magical power, depending upon the dimension, of a harmonic function. All right, so this is written in this way. This is a very nice metric, and by the way, you could easily generalize this now to have conformally flat, scalar flat, and as many ends as you like, just by adding a lot of Green's functions terms for different points. On the other hand, so the most naive thing you could read off about this is it's saying that the metric has this kind of expansion where the mass comes up as a coefficient of 1 over the radius to the n-2. And so this, if we think about how this behaves at large radius, this is a naive version of the mass that people often use. Many of the first mathematical papers assumed that we're only looking at metrics which are of this form plus lower order terms. Notice, though, that the power of the radius that comes up here is the dimension minus 2. And I allowed in my definition before for this to be actually to a much lower power, n-2 quantity over 2. So in fact, while this is a nice model, you don't need to have such rapid fall off in order to be able to define the mass. All right, now let me give you another important example, and it's one more pertinent to the real topic of my talk. This was an example that was first discovered by Dan Burns. And it played a big, when he told me about it, he never published it. It appears in one of my papers where I named it the Burns metric. So here, this is a metric on the blow-up of C2 at the origin. There's a standard way in complex geometry where if you have a complex manifold, you can replace one point by a hypersurface which looks like complex projective space of one lower dimension. Let's do this in complex dimension 2. So you now look at, this is just the so-called tautological line bundle over CP1. CP1 consists of directions, complex directions in C2, and you can now take the fiber at a given complex direction to be the span of any vector in that direction. So that's to say you get a way of, so this is a line bundle over CP1, which by definition is a subbundle of the trivial rank 2 bundle. And it has a natural projection to C2, which crunches the zero section shown in green here to the origin. It's replacing the origin with all of the complex directions through it. Now, here I'm emphasizing that this sits as a complex hypersurface in C2 times CP1. And there's you could do the following naive thing. Give CP1 its usual round spherical metric. Choose your radius. You have a choice of how big it is. Choose the Euclidean metric on C2, and now restrict that metric to this complex hypersurface. That's an example of a Kähler metric. Kähler metrics restricted to complex submanifolds are still Kähler, and I'll tell you what Kähler metrics are if you don't know. But the amazing thing discovered by Burns is that this has, the scalar curvature is exactly 0, and this is asymptotically Euclidean. What is Kähler? Well, there's an important notion in Romani and Geometry is of the holonomy group of a Riemannian manifold. If you choose a base point and look at any piecewise smooth loop, you can drag vectors around the loop, trying to keep them pointing in the same direction as you go along. What you'll find is that if the manifold is not flat, usually a vector will come back pointing in a different direction. And this associates to every piecewise smooth loop at the base point a linear map from the tangent space to itself called the holonomy transformation associated with the loops, with the given loop. When you look at the set of all such transformations arising from all such loops, you get a subgroup of the orthogonal group. These all, the way that you drag vectors in Romani and geometry preserves length, so these are always orthogonal transformations. But you get a so-called holonomy group associated with a Riemannian manifold. Kähler metrics are exactly those for which the holonomy is a subgroup of the unitary group. Another way of saying that is that if you think about this vector space as a complex vector space in the right way, these transformations are all complex linear as well as real linear, as well as preserving the inner product. So they're unitary. Remember, the unitary group is the intersection of the orthogonal group with the complex linear maps. That makes this tangent space a complex vector space, but in fact, by dragging it around parallel, you get an almost complex structure on every tangent space. And it turns out then that this is integrable in the sense of Newlander-Nierenberg. So the fact that there's a torsion-free affine connection that preserves with respect to which J is parallel implies that it's integrable. And in fact, that's an if and only if statement. Here, this is actually, though, the Riemannian connection, and it also has the property that the metric is invariant under J. That's exactly a characterization of Kähler metrics. It's one that Kähler would have never recognized and which you don't find in most books on the subject that were written in connection with, say, algebraic geometry. But this Riemannian characterization is the same as saying that we have a complex manifold, we have a 2 form which is invariant under the action of J, and such that when we cook up a metric by plugging J into one factor of the 2 form, we get something positive definite. Here, so there's an associated closed two-form. So we get a closed two-form and an integrable complex structure. Omega is called the Kähler form of the manifold, of this Kähler manifold. It's a closed two-form, and in particular, it has a de Rham class, which comes up. So the Kähler's definition of a Kähler manifold was, let's do the following stupid, crazy thing. On complex Euclidean space, take some function, take its mixed partial derivatives, think of that as determining a Hermitian matrix that determines a positive and definite inner product in the manifold. Here's some weird class of Riemannian metrics. But what Kähler discovered, and so here this, in general, this is a local form for a Kähler metric. The F would be called a local Kähler potential. The Kähler form is also expressible in terms of second partial derivatives of this F. But what Kähler discovered that made him believe that this was an important class of metrics is that when you compute the Ricci tensor for these metrics, it takes the same form as the original metric. It also is represented in terms of mixed partial derivatives. And he thought, well, maybe it would be easier to understand Einstein's equations, either to say that the Ricci curvature is 0, or maybe Ricci curvature is a multiple of the metric for this particular class of metrics. And that eventually led to the work of Calabi and Yau. Yau got the Fields Medal for showing the existence of lots of Ricci flat Kähler metrics using some of these ideas and a lot more deep mathematical ideas. So Kähler's contribution was, in a way, to do something crazy and realize it wasn't so stupid. But from a modern point of view, the magic that's going on these manifolds is that the Ricci curvature is actually related to a two-form, which is the curvature of a line bundle, named the canonical line bundle on the manifold, the forms of type M0, where M is the complex dimension. Okay, so a very important thing in Kähler geometry is that the de Rham class of this closed two-form is called the Kähler class of the Riemannian manifold, and it's an important invariant. One often studies the class of Kähler metrics in a fixed Kähler class. Another point of view is that this closed two-form is non-degenerate, has maximal rank. And such things are called symplectic manifolds. They are related to the classical theory of Hamiltonian dynamics and have led to a very, very rich modern subject of symplectic manifolds. So that is something which is closely linked to Kähler geometry. All right, so the amazing thing here is in this particular example of a Kähler metric, we just took the obvious product metric on Euclidean space times CP1, restricted to the tautological line bundle. It turns out, lo and behold, Burns made the computation, and it turns out the scalar curvature of that metric is exactly 0 in complex dimension 2. If you write down, if you want to now write down the Kähler form of this metric explicitly, it takes the form of the mixed partial derivatives of u plus 3m log u, where u is the Euclidean radius squared, and here m is the mass. All right, so here I've shown you that there's some interesting examples of asymptotic. This is an asymptotically Euclidean. The Burns metric gives you an asymptotically Euclidean Kähler manifold, where the mass has some interesting meaning. It's related to the size of the throat. It's kind of analogous to the picture in the classical Schwarzschild solution. But there's an interesting generalization, which is to consider rather than requiring the ends to look like copies of Euclidean space, we could instead allow the ends to look like quotients of Euclidean space. In this case, the manifold is said to be asymptotically locally Euclidean. So here we have conical ends, which are cones on spherical space forms, and we mod out by groups of isometries of Euclidean space. With this, so we might have different ends that have, because of the dimensional reasons, the group you're modding out by is actually the fundamental group of the end. But the fall-off conditions are the same. Why one would consider? I should mention. So why are these called ALE spaces? It was discovered by Hawking and his group, and they were drinking beer at the time. So, so they're often called Alspaces, but ALE is the way I'll pronounce it. So why consider ALE spaces? Hawking and his group discovered some so-called gravitational instantons that are non-trivial Ricci flat Kähler manifolds that come out of this. These turn out in modern Romani geometry to play key roles as bubbling modes for sequences of Einstein metrics on compact manifolds. When you have curvature concentration and you rescale, you can see such things. And there's a similar thing for scalar flat Kähler surfaces, and they arise as bubbling modes for more general sequences of so-called extremal Kähler metrics. In fact, this kind of technique can be used to construct some compact Einstein manifolds. All right, so now mass is still meaningful in this context. You take exactly the same definition as before, and the only difference is that by convention I'm going to take the integral to be on the quotient of the sphere rather than on the sphere itself. If you wanted to insist on passing to this universal cover of the n, that would introduce an extra factor, but it turns out to be better to do it this way. And you have the same issues as before. Is this well defined? Is it coordinate independent? All right, so now early in the talk I mentioned the positive mass conjecture. And the positive mass conjecture is that if you have an asymptotic Euclidean manifold and it has non-negative scalar curvature, then the mass should be non-negative. When this was first told to differential geometers, they were very puzzled why this should be true, but physicists had a reason for believing this to be true, because the scalar curvature in this context actually represents the local matter density. And it's saying that if you have a universe made up of locally attractive matter, so the matter density is non-negative everywhere, so the local gravitational effects are positive, then the net effect should also be positive. So the total mass should be greater than or equal to 0. Schoen and Yau proved this first in dimension 3, and then they realized that their proof worked up through dimension 7. Their proof involves a reverse induction where you lower the dimension, but it involves the theory of stable minimal hypersurfaces, and it turns out that things go wrong in high dimensions. Witten gave a completely different proof. His proof was also in dimension 3, but people immediately noticed it worked in arbitrary dimensions as long as you assume that the manifold is spin. Schoen and Yau very recently came up with a repaired version of their proof which avoids the previous difficulties. And well, the paper has not been accepted for publication yet, so let's say maybe I could put a question mark in, but I think that the consensus is the paper is probably right. So I guess when I made these slides, Shane was in the audience, so I didn't want to put a question mark. But I think it's probably right. But anyway, let's wait. As they say, the opera's not over until the fat lady sings. Let's see if it gets into it. If the referees really give it a thumbs up. All right, Hawking and Pope, in a different direction in the 70s, made a conjecture that this theorem should be true in the ALE case. So instead of assuming the manifold looks like Euclidean space at infinity, suppose it looks like a quotient of Euclidean space by a finite group at infinity. However, I then discovered counterexamples to this in 1986. And the particular counterexamples I found were scalar flat Kähler metrics. In fact, I was interested in scalar flat Kähler metrics as scalar flat Kähler metrics and as anti-self-dual four manifolds. The first time I submitted the article, it was rejected, and then a colleague, Mike Anderson, said, well, do you know about this conjecture? No. Why don't you calculate the mass for these? And it's usually negative. I sent it back to the same journal. It was immediately accepted. And the reason I tell you this story is if you're young and and nobody knows who you are yet, you may have this experience, who is this person? Let's throw away the article rather than accepting it. I'm glad that they rejected it, though, because it was a much better result after having calculated the mass. So the particular examples I found were on, they were line bundles of Chern class less than or equal to -3 over CP1. So what can one say about the mass of ALE Kähler manifolds? Well, there's a useful lemma, which is that such a manifold only has one end. I said at the beginning, maybe you might have many different ends. In the Kähler context, it's excluded to have more than one end. So the picture is like this, rather than something more complicated. By the way, the proof of this is more subtle in dimension 4 than in higher dimensions, and because crucial fall-off is very, very weak in dimension 4. To improve this, to actually get a proof of this by these kinds of techniques, I had to use some methods of symplectic topology. So it's in the second paper. In the first paper, we assumed something stronger than crucial fall-off. And so it would have been more complicated to say what the hypotheses were. But the upshot is that in the Kähler context, ALE manifolds only have one end. And so you can say, what's the mass of the manifold rather than the mass of the end? There's exactly one end. All right, so in terms of the main results, one of the main results is in the case when the manifold is actually scalar flat Kähler and ALE. And it's the statement is that the mass is a topological invariant. Namely, it's determined by just the smooth manifold, the first Chern class, and by the Kähler class. Now, in fact, the way this is proved actually produces a specific concrete formula, which I'll show you in a moment. But because there's a concrete formula, you can just, it was actually kind of hard, calculating the mass as this limit, it seems very complicated. But after you see this formula, you can just look at things and say, oh, I know what the mass of that is. And so it's almost no work now to compute, to see, for example, that my counterexamples with negative mass were counterexamples. And in fact, we immediately got the following nice corollary. If you have an ALE scalar flat Kähler surface, that's where it's complex dimension 2, and if it is obtained as a minimal resolution of a surface singularity, so it has no -1 curves, if you like, it's not the blow-up of another resolution, then its mass is never positive. And in fact, it's 0 only in the case when it's Ricci flat. So minimality is essential here. When you blow such things up, and it turns out that the mass can change sign. All right. So here's the explicit formula that Hajo and I found. And in order to explain it, I have to first point out a topological fact about these manifolds. The natural map from compactly supported de Rham cohomology to de Rham cohomology is isomorphism in these cases. This is actually a topological fact. The compactly supported de Rham cohomology it's essentially the cohomology of the manifold modulo the end, relative to the end. But in terms of de Rham cohomology, you state this there's a complex of compactly supported differential forms. You can look at its D defines a co-chain complex on it. You can look at its cohomology. It turns out whether you use compactly supported forms or all smooth forms, you get the same cohomology on these manifolds. So in particular, well, there's a natural map from compactly supported forms to forms that induces a map from a compactly supported cohomology to cohomology. But in this case, it has an inverse. And our notation is club, or club suit. So the idea is if you're given a closed form, club it over the head until it's compactly supported, and then take its compactly supported cohomology class. So this is the inverse of the natural of the natural map from compactly supported cohomology to cohomology. All right, once I've stated that, then I can state what our formula is. It is that for an ALE Kähler manifold of complex dimension m, and I'm sorry I'm using m in blue for the complex dimension because m in black is the mass. Different font. That was quite dangerous when we were going through galley proofs. So the mass, and also the manifold is called m. Well, at least it's capital. All right, so the mass of the manifold has one contribution, which is the integral of the scalar curvature times a certain coefficient that depends on the dimension. And the other contribution comes from taking club of the first Chern class paired with omega to the m minus 1. So when you have a compactly supported cohomology class, it pairs with any regular cohomology class of the same of the appropriate dimension. And then there's a conventional factor depending on the dimension also. It's important to notice that this is a minus sign, this is a plus sign. All right, so here again, the scalar curvature is being integrated with respect to the metric volume form. There's nothing funny about this. It's a geometric thing. The first Chern class is the first Chern class of the almost complex structure of the manifold, and omega is the Kähler class. And here we're taking, there's a natural pairing between compactly supported second cohomology and codimension 2 cohomology. So here's the formula, but you might massage it into the following way. If you multiply it by some other factor, the mass is basically the difference between the integral of the scalar curvature and a certain multiple of C1 paired with omega to the m minus 1. People that do Kähler geometry might remember that the scalar integral of the scalar curvature on a compact Kähler manifold is exactly a multiple of C1 paired with omega to the m minus 1. So that you have an identity, that this kind of expression is 0. If you look at the corresponding expression, well, on a non-compact manifold, C1 doesn't naturally pair. You have to club it over the head before it pairs. But other than that, what this is saying is that the mass is an anomaly that measures the way that the formula for compact manifold fails in the non-compact case. There's an extra term, the mass. It's a boundary correction to this formula. And in fact, while I'm not going to say anything about proofs, that somehow the proof captures this idea. Okay, so one corollary is the first theorem. If the scalar curvature vanishes, you get a topological formula for the mass, because the integral of the scalar curvature is obviously 0. And I'm going to jump through. I was going to work out some examples, but I'm short on time. This is supposed to be an hour talk. I'm over time, so I will jump through the examples. I wanted to show you that this actually computes interesting things. But anyway, let me just now go to the last results. The positive mass theorem follows from this formula for Kähler manifolds. So when you're in the Kähler case, you find that if you have an asymptotically Euclidean Kähler manifold with non-negative scalar curvature, it has non-negative mass. And mass 0 happens only for Euclidean space. But in fact, our proof shows something stronger that is rather, so you might say, well, now there's no point of this because Shane and Yao have a more general theorem. But in fact, what our proof shows is something stronger. It's a Penrose-type inequality, and it says the following. If you have an asymptotically Euclidean Kähler manifold, let's suppose it has scalar curvature greater than or equal to 0, then there is a canonical divisor of D, and it's actually numerically canonical in general, but it's Poincare dual to minus C1. It's written as a sum of compact complex hypersurfaces with positive integer coefficients. The union of these hypersurfaces is not empty unless the manifold is diffeomorphic to Rm. And in terms of this divisor, the mass is greater than or equal to the volume of the divisor, counted with multiplicities and times a certain conventional factor depending upon the dimension. So this is like in the example of the Burns metric, the mass was measuring the size of the 0 section. And here it's the same kind of thing. In fact, when it's scalar flat Kähler, this is an equality. So this illustrates the way that you can actually look at such manifolds and read off what the mass is for scalar flat Kähler manifolds. All right, so here's the main result. This mass formula for ALE Kähler manifolds, and a picture to remind you of what kind of manifolds we're looking at. So finally, merci aux organisateurs et à l'Institut Fourier de m'avoir invité. C'était vraiment plaisir d'être ici.